entitled High-Level Synthesis of Functional Patterns of Lift. I'm so sorry. I'm so sorry. Martin Kristen, University of Edinburgh.
Hello everyone, thank you for staying until the very end. Sorry? Yeah. Right. So my name is Martin, I'm from Edinburgh, Scotland. In this work we try to extend the lift project, some of you might be familiar with. But in the title there are three terms. Well, basically just do high-level synthesis and lift. So I'm going to explain those terms in this order. But first, I just want to present the common problem we all have, and many of the other talks address the same issue of having applications on one end, and people maybe not knowledgeable in computer science, but data scientists who want to use all this hardware and performance that is available, but it's not accessible. And on the left, we have the CPUs, which are familiar to almost everybody. They are easy to program. They are general purpose, which makes them a bit slow or energy inefficient. And on the other side, we have the FPGAs, which are very efficient in terms of how they consume energy, but they are extremely hard to program. In the middle is GPUs, and on both ends, it's somewhere in the middle. And we want to bridge this gap and have the best of both worlds in this project. But first, let me introduce the FPGA as a concept. The way how to view it from the execution point of view is a hardware, as a circuit of logic gates and bits and wires connected. But the implementation can be changed at runtime. So that's what the Field-Programable stands for. And it basically, how it's implemented is a series or a grid of lookup tables, which can be programmed to express functions as an input to output mapping. And then some interconnect, which when we wire it together, it basically computes the tensor graph process. But this is performed at bit level. But you can view it as a data flow through nodes of functions. I also included these blocks, these tiles labeled DRAM, which just stands for the memory that is stored on the FPGA fabric itself. So it's not directly accessible to the CPU as normal RAM would be. As an example, if we have a logic diagram composed of gates, the compiler can somehow identify some clusters of these operations, of these functions, and wrap them together into individual lookup tables. So each circle here can represent a single lookup table that maps the ABC inputs to the outputs, to the three outputs values or wires. And by programming the interconnect, it would be the signals would propagate to the next functions and lookup tables. So the advantage is that the FPGAs can be really fine-tuned, and if we have in our application the need for specific, for example, data type, I would say 5-bit integers that we want to use in our convolutions, then FPGAs can really use just 5 bits and no more. And this specialization results in high power efficiency as opposed to general purpose CPUs. And you can imagine that this really is a good fit for array processing, as arrays are of course very regular in how they're going to be processed and how the memory is accessed, which gives a good deal of scope for the specialization, resulting in good efficiency. Also, recently we see all of these big companies moving to the FPGAs as well, introducing them to their cloud systems and platforms. But the problem is they, as I mentioned, are not accessible to programmers. So what you see here is an ugly code. It's called VHDL code. It's a hardware description language, and you can use this code to really generate printed circuit boards or real hardware. But this is what is the interface for the FPGA programming as well. And all of this code is just to add two numbers. So this is far from accessible to ordinary users. And if you want to really extract the performance from FPGA, you need to have good knowledge of hardware design. So let us step back and look at the overall goal of the LIFT project as we envision the future. On the top we have the application, the users, the data scientists. They can perhaps use libraries that implement their convolutions or specific kernels they want to execute. But where we start in the LIFT project is the intermediate representation of the program. So what we focus on in the design of the IR is data parallelism, and I'll introduce the individual bits of LIFT that can be performed, can be expressed in this language. But LIFT is also the implementation of this IR and the compiler. And the important step here to notice is that it can target different platforms. In this work, in particular, we target the FPGAs through the VHDL language, but previous work has focused on OpenCL, GPUs, and some CPU code as well. So in LIFT, we designed this around functional programming. We have these higher order functions and functional patterns that probably most of you are familiar with, like map, reduce, all of those that would see in regular functional language. And we get from these patterns at the high level by rewriting into specific patterns that are tied to the implementation and the target platform. During this exploration, we can try different implementations, how to structure the work groups on GPUs, or how to perform transformation, mapping, compositional functions. And through some process, we can select the best implementation that we come up with, resulting in a program that is expressed using the low-level expressions, and these are specific to the platform. So we would have different low-level expressions for FPGAs than GPUs, and there, after that, is a straightforward process to generate the code that will be run. So in this work in particular, the focus is on the design of low-level patterns and how to generate the VHD code out of it. As a working example, I take dot product, which is expressed here using just zipping two vectors, then multiplying the elements together and altogether reducing with a plus operation. And you can see this as a data flow in a functional sense, as a, if you imagine TensorFlow or graph processing. And that's how we want to start with converting this into hardware as well. So the first thing I want to introduce is the basic data type of all the tensors that we're going to propagate through the functions. And we use streams with streaming protocol. In hardware, you can imagine all these modules, all these boxes of hardware being connected in a producer-consumer fashion. And they always communicate data and a few control signals which are with respect to the streaming protocol that we're going to employ. And as a working example, if I try just to transfer this array from producer to consumer, the producer can just set the first element on the data bus and assert the valid signal to indicate to the consumer that the data is ready. And once the consumer asserts ready, the data is being transferred. The next data moves on. But the consumer can at any point stop the transfer by saying, I'm not ready now to consume next piece of data, and the producer needs to wait until the consumer is ready again. Similarly, the producer can indicate the next piece of data is not ready. And this is how the communication of the streams of the tensors is synchronized without any need of global communications or scheduling. So we got the data type covered, and now we need to convert the high-level patterns into low-level patterns. So these are all we need for now, and some of them are used, the first to move the data around from the regular RAM to the FPGA memory, or the fabric of the FPGA. Some of them are just streaming versions that operate on the data streams of the already existing patterns, like the reduce stream or map stream. And the others I'll explain later. So we can start rewriting our expression for dot product just by moving, the first step is to move the data to the FPGA. So on the left side, there's the CPU side, the software. And using two FPGA pattern, we move the data to the FPGA fabric, where it needs to be split into one and the other input. And whatever the FPGA produces at the end of the day, we can move back to the CPU, to the software side. So we can zip these two streams, these two data flows together to just reflect the functional expression that we have. And next step is to rewrite the map using map stream. The mapping, all it needs to do is to instantiate the operation that we are trying to map for each element, so that the function is applied to every element of the data stream passing through. And then we reduce it. So this is a typical data flow you can imagine, with some accumulator variable that is being updated by the next input until the last input is detected, where the output is produced and then moved to the CPU side. So here you can notice that the hardware that we generate, this is not some von Neumann architecture, so we don't have instructions. We don't need to fetch the next instruction, then decode it and execute it. We really express the program directly in hardware using these data flows, connecting it together, using only the functions and the operation operating on the data that we need in the program. And this is the power of specialization that results in the performance and energy efficiency. So, in this example, you might notice that it seems like you would access one element from U and one element from B, and then continue with another element from U and another element from B. You can imagine this is not very efficient, as the access to the memory is just jumping from one location to the other. So instead, what we introduce to wrap it around is a let pattern, where all it means is that we would store one of the vectors, the U in this example, on the FPGA fabric, so that we can stream the U vector first, store it on the FPGA, and then we stream the whole of B vector to the FPGA. So after coming from the storage on the RAM on the FPGA, we can label it as X, as in the program, and you can imagine this might be much faster in terms of execution time. We take this as a baseline implementation for everything, because the original way doesn't make even sense. So, one of the further optimizations that we can perform is vectorization, which just means we do more operations in parallel in space. And to do that, we just convert at some point the string to a vector format, where each data bus would now contain two elements of the array, not just one. And then the mapping can be converted to mapping over a vector, which would need to instantiate two hardware modules performing the multiplication, and we can convert back to keep the rest of the system type safe and type fluent. let's look at more involved and interesting example, matrix multiplication. In the lift, it's very easy to express, as you can imagine, just as two maps where you iterate over rows and columns and use the dot product together. So here I assume the second matrix B is already transposed. But we can use the same process of converting individual patterns to the low-level patterns as we saw with dot product, and we result with this diagram. So if we follow through the example, the A matrix, the first input, is first streamed onto the FPGA and stored in its entirety on the block RAM on the FPGA fabric. So now we have the whole matrix A stored on the FPGA, and then we start sending the second input, but we don't store it, we first split it. So splitting is basically converting the flat representation of the B matrix into its columns by creating this multi-dimensional stream. And then for each column, we just store in the block RAM a single column of the B matrix. So now in these two block RAMs, we have matrix A and one column of B. And then what happens here is basically matrix vector multiplication. That's the purple box. Now, another optimization we can perform is coarse-grained parallelism, where instead of storing one vector or one column of matrix B, we would store two columns of matrix B at the same time, and we can perform now two matrix vector multiplication at the same time. So in this parallelism, we can employ more of the resources available on the FPGA, resulting in better performance. So we have some evaluation numbers to show you. And first, to introduce the platform, notice this is a tiny board. So it's only used for prototyping as a proof of concept. The CPU side is dual core, and the one thing to notice is the difference in the clock frequency on the FPGA and the CPU, which will be important later. So we only evaluate matrix multiplication because for the dot product there is not much scope for improvement in terms of data reuse and how we structure the algorithm. But in the diagrams I'll show the throughput on the y-axis in giga operations per second. So the higher the better. First we start with the baseline that I showed you before. So this is matrix multiplication diagram without any optimizations, so no vectorization and no coarse-grained parallelism. Then we introduce the vectorization with a factor of 2. So now we can perform operations on 4 elements at the same time. And this is nothing but changing the dot product implementation to operate on this vector. So in terms of the rewrite of the expression in lift, it's quite simple. And finally, we can add parallelism on top of it with a factor of 2, and we even get better performance. You can see it doesn't scale linearly, and that's because there is some overhead always involved in converting the data or waiting for both of the implementation to finish and then serializing the transfer of output back to the CPU side. At this point, in terms of adding the parallelism, in terms of these two optimization, we run onto the kind of the performance limit of the FPGA, because each of these optimization requires more resources from the FPGA to be used, and we didn't have any left. Now we compare the same application, but with different input sizes, and we also have different implementations to compare against. One thing to note, the first CPU implementation running in software purely is just for comparison. It can be really compared because it's different hardware altogether. But just to see that we can do better than in this platform that we have just using FPGA. So the C naive is just a serial version where you would have 3 loops nested, iterating over each other. And it's quite slow. You can see performance degrading with larger inputs, maybe just because of cache effects. Then we have the optimized version of C, which is parallel, because the CPU we had offers 2 cores, and also it's cache aware. And we already get magnitude better in performance. So just to note the y-axis in logarithmic scale here. Now this is interesting. This is the FPGA version provided by the board's manufacturer. So this is the high-level synthesis tool, Vivado, which is just the recommended version of doing matrix multiplication on FPGAs for this particular board. Also, you can notice that the performance is almost identical as the C optimized version, which is running on dual core with about at least 3 times higher clock frequency. And the FPGA still can match it. And now in the lift implementations, we even get 1 order of magnitude better performance, which is mainly due to better utilization of the hardware on the FPGAs. So we attribute this mostly to the optimization of vectorization and core-grain parallelism that we saw before. So the takeaway point is that lift, as it stands now, is a much better way to generate code for FPGA. It's lots of work to be done still, but now we don't need to write the VHDL code anymore. We get good performance, outperforming the state-of-the-art for the board that's been provided. And this can be viewed just as a stepping stone towards the full, realized, robust platform in lift. And that's what the future work will focus on, where we want to introduce better cost models for the FPGA and the hardware we generate, so that we can explore the space, reason about different implementations. We want to have even more patterns to express different operations. So, as we heard before, it can express stencil computations or convolutions and all different kinds of parallelism and data parallel applications. So, for the moment, the main focus is on convolutions. But I'm excited about where this project is heading, and I'm sure we'll hear about this more in the future. So thank you.
So for your C naive and C optimized, what exactly is the difference? For example, are you using the dot product as your naive C, or you did move the loops out to the outside as the naive C? So what is the difference?
So I didn't write the C code myself exactly, but the main difference is that C is sequential and it's the naive approach, so it wouldn't have any loop transformations. The optimized version should be hand-tuned, really extracting the best performance, what can be extracted using cache awareness, the parallelism using the dual-core processor.
So the C implementation was from ARM PR's implementation?
Sorry?
It's some library that you downloaded, or something you've written yourself? Somebody in your team wrote themselves?
I think it was written by hand.
In this graph, do you have any feel for the peak performance that you can get in principle for this problem or for this architecture? How far away are you from the absolute maximum?
That's a very good question. We don't have an estimate. What we have is this utilization at the end. So the one thing to notice is the kind of the hardware acceleration on the FPGA, which can perform much faster multiplication or operations, the additions, than if you were to synthesize those algorithm unit in the FPGA fabric. And we can see that we utilize it much better, this resource in particular, than the high-level synthesis tool we compare against. So maybe there's the answer in the theoretical limit, that if we manage to utilize 100% of this, that's the peak. Of course, it's not realistic to expect to scale that well, because in any implementation you will have some overhead of moving the data around. So,
maybe follow up. Do you have any heuristics on balancing between the exhausting all the resources and replicating parts of your pipeline? So, I mean, you always have a choice whether to replicate more or in which place. So how do you figure out where to put the effort when you generate hardware?
So at the moment, this cost model is not fully automated in the lift, and we did a lot of this by hand, trying whether the generated code has still enough resources to be actually realized. But at different points, we run into different resource limits. For example, what I show here, the kernel size of the FPGA is always the small size of the matrix multiplications, and the others are using tiled versions, where the tiling would be performed on the host, and only the kernel of this size would be run on the FPGA. And that's an example where we run into the memory limit of the FPGA, the capacity of the block RAM.
I think my question goes in the same direction as here. You had your optimization were parameterized by some integer values. For example, 4 for the vectorization and 2 for the parallelization. Did you pick these values by n?
Yes.
And how do you aim to optimize them? Because that's most important point by this. I think that not the program has to choose these values, that is fully automatically, right?
Yes, that's the subject of future work, to optimize this process to pick the optimal values.
Do you have any idea how to do this? Because right now I don't see how you can do this automatically. Do you want to make an exhaustive search or something like that, or a search space, or?
So the lift has experience with using heuristics or machine learning heuristics, and even brute force approach in some scenarios in the early days of lift was used just to generate as many different implementations of the same program, and then trying them out which one runs the fastest. However, with FPGAs, of course, we wouldn't be able to compile the code of different versions and run them in a reasonable time. So what we're planning to do is to employ some cost models. So we all need to know for individual platforms what is the number of resources of different kinds and how our design utilize those resources, and whether it would all work together, and what would be the expected, at least approximate performance of that.
I think your framework relies on these functional higher order patterns. Do you infer those from code, or does the user have to really target those kind of patterns when they write the input source code or maps?
The user needs to use those patterns directly, and that's what the high-level, very high-level top of the lift should be. So it relies on these patterns, but it should be usable for the user and well readable. That's why we chose the functional language, functional patterns.
So how far from state of the art? I mean, if the hardware you were running on is probably not state of the art, right? So
yes.
will the figures change when you go to more modern FPGAs, or at least CPUs? Or what is is there a story there? Or?
That's the work in development now. So this this was the prototype project and preliminary work. Now we're working with one of the higher-end FPGAs, comparing with different platforms and doing this interesting work. But our ambition and expectation is that